Okay, gentlemen, welcome to section 5.2, special products. This first question asks us what the degree of this expression is, basically. And first you need to recognize that it is a trinomial. There's one, two, three terms connected by addition or subtraction. What we want to do is to find out what the degree of the entire polynomial, in this case a trinomial, to figure out what the degree of the entire polynomial is, we want to look at each term within that trinomial and find out what degree each term is. Whichever of those three terms has the highest degree speaks for the whole bunch, basically, or speaks for the entire trinomial. So if I look at the first term, there's an exponent 3, there's an exponent 4, and there's a little imaginary 1, I guess you could say, on the C. So altogether, that has a degree of 8. You look at the second term, we have an 8, an imaginary 1 on the B, and 1 on the C, so for a total of 10. And on the third, we have 2, a 3, and a 4, for a total of 9. Because 10 is the highest degree of the trinomial, term of the trinomial, then that is the degree of the entire polynomial. Moving on to the second question. Which expression represents the surface area of a cube with side measuring x plus 1 units? So basically, if you have a cube, we're talking about the length, width, and depth, each being x plus 1. In that case, if we're trying to find the surface area, then we would want to find the surface area of one face, for example. There are 6 faces of a cube, and each will have the exact same surface area. In this case, the surface area of one face will be x plus 1 times x plus 1, which would be x plus 1 squared. But there are 6 of those faces, so we're looking for something that has 6 times that, and of course, that's answer A. Simplify fully without a calculator. This question is basically just asking you to see if you, this question wants to see if you know how to cross reduce. So first off, we're going to make that 25, because 5 squared is 25. And then in terms of cross reducing, we are going to look at 25 divided by 25 is 1. And I'm going to cross reduce that with 75. 75 divided by 25 is 3. Then we'll look at 9 divided by 9 is 1. 90 divided by 9 is 10. Not bad. We can also do, in fact, let me go backwards for a second here, because as I'm doing this, I'm seeing a better way. 9 divided by 9 is 1, but 9 times 6 is 54. And then 45 and 90 work well together, because 45 divided by itself is 1, and of course 90 divided by 45 is 2. Then we can continue to cross reduce. I'll use a different color here, but you can continue to cross reduce. The 3 divided by 3 is 1, and 6 divided by 3 is 2. And now I've got nothing else left to cross reduce. The denominator is a 1, and the numerator has 1 times 2 times 2, which is 4, or 4 over 1. And that's it. The learning goals here are how to square a binomial and how to factor and expand a difference of squares, or a short form for that would be DOS or DOS. Okay. Use a distributive property to find each binomial product. This is a blast from the past for lesson 5.1 when we learned how to multiply polynomials and find binomial products. So x times the x gives us x squared. X times negative 5 gives us negative 5x. And then positive 5 times the x is positive 5x. And then positive 5 times negative 5 would be negative 25. These two terms are like, and if we add them together, they eliminate each other. So we are left with x squared minus 25. And the reason why we call that a difference of squares is because the subtraction in the middle is where we get the word difference from. And squares, we have x squared and 25. And both of these are perfect squares. So therefore, we call it a difference, the subtraction of two squares. Let's look at, so again, I want to point out something here. If you look over here at A, we have the exact same binomial being multiplied but one has an addition and one has a subtraction. That is what a difference of squares looks like when it's been factored. And what we also would call root form here. When it's not in root form, or what we call standard form, then as you see here, we have x squared minus 25. That's what a difference of squares looks like when it's not factored. What we have here is x plus 7 squared. And as you know, this is really x plus 7, or whatever's in brackets, times itself. So x plus 7 in this case times x plus 7. If we expand this, we will get x squared plus 7x plus 7x again, and then plus 49. So the x times the x times the 7, 7 times the x, and 7 times the 7. If we collect the like terms here, we have x squared plus 14x plus 49. Now there's a little trick. So I'm going to erase this and show you something again. There's a little trick with this that may help you. When you are multiplying something by itself, okay, you can square the first term. You'll take a notice that the first term squared, because I'm applying the square to it, ends up being x squared, right? The last term, let me just erase that. The last term is a 7, positive 7, and the positive 7 squared gets us our 49. And to get the middle term, this positive 14x, one of the shortcuts or a little trick you might recognize is if you take the, if you take this x and you multiply it by positive 7, you get 7x. And double that. If you double that, you get 14x. So again, I'll give you a different example. If I were to do, let me just use the space over here. If I were to do x plus 3 squared, a shortcut would be to square this, and I'll get x squared, square the positive 3, which would get me a positive 9. And the middle term, I'm going to multiply x times positive 3, which is 3x, and double that. And I'll end up with plus 6x. And this is what we call a perfect square trinomial. And I believe I speak to that down here further at the bottom of the page. We'll get into that again. So let me just point this out. A perfect square trinomial, unlike a difference of squares, and somewhat like a difference of squares, a perfect square trinomial has 3 terms. You'll notice the difference of squares only has 2, x squared minus 25. Here we have 3, but the first term is a perfect square, x squared, and the last term is also a perfect square. That's how you can recognize a perfect square trinomial. You'll also notice by looking at this or by looking at this that a perfect square trinomial is really vertex form. So a vertex form is really a perfect square trinomial. All right, here's a little bit more of a difficult question. The radius r of a circle has been increased by k. Both r and k are measured in the same units. Write a formula for the area of the new circle. Well, you already know that the area of a circle is pi r squared. But this new circle, this radius, has been increased by k, whatever that amount is. In that case, we have the area of the circle is now pi times radius plus this amount k squared. If we want to expand and simplify, as the question tells us to do, then we are going to first, I will leave the pi alone, and I'm going to work on this perfect square trinomial. So I know that the first term will be r squared. The middle term will be r times k, which is rk, but I'm going to double that. So it'll be plus 2rk, and then plus k squared. I'm not happy with that, so let me fix that. Plus k squared. Now I'm going to distribute the pi throughout that trinomial. So I'm going to have a equal pi r squared plus pi times, let me go backwards here for a second, plus 2 pi r k plus pi k squared. And you may notice that you have a perfect square and a perfect square, and that's one identification of, or one factor of, or characteristic, sorry, of a perfect square trinomial. So x plus 5 times x minus 5 is an example of a difference of let me squeeze this word in here better. Difference of squares, and x squared plus 6x plus 9 is an example of a perfect square trinomial. And moving forward, we'll refer to those as PDOS and PST for perfect square trinomial. And the reason why x squared plus 6x plus 9 is an example of a perfect square trinomial is because x plus 3 squared is equal to x squared plus 6x plus 9. And you'll remember that from the example I gave you right here. Okay? And your homework is on the screen. Good luck, gentlemen.